I'm very much looking forward to hear the talk from Dr. Shulman, the head of Fraunhofer Institute on Cybersecurity in Darmstadt. And the floor is yours, Haya.
Thank you very much for the introduction, Reinhard. Just a small correction. I am heading a Cybersecurity Analytics and Defenses division, and I had the mission for Cybersecurity Analytics and Defenses in the German Federal National Cybersecurity Center in Darmstadt. So what I will tell you today, my name is Haya Shulman, and what I will tell you today is about digital resources in the internet, what they are, and how can we validate ownership of digital resources in the internet. So let's dive in. Right, here's an outline. My talk will be split to 3 parts. One is what are digital assets, and then I will talk about one example for digital assets is IP prefixes, how you do attacks, what are the vulnerabilities, and what should be done for defenses, and the same for domains. And then conclusion. So what are digital assets? Essentially, modern societies increasingly leverage the internet to access different services, if it's medical services, if it's voting, critical infrastructure, electronic autos, anything that you can think about. TV, smart TV is nowadays over internet, and these services are hosted in the internet on IP addresses and can be accessed via IP addresses or domain names. So these are the 2 digital assets, the most popular and most widely used digital assets in the internet. Now, to be able to access a digital asset, we want to ensure that our communication is protected. Think about a situation, a common situation which we have every day. We perform different transactions in the internet, we do purchases, and think about a client who accesses eBay. You send your credit card details, you want the communication to be protected against cyber criminals or government sponsors, attackers. So we want to ensure that our communication is protected. This is the first goal. And the second goal is we want to ensure that we access the correct resource, right? When we protect the communication, if you protect the communication to the attacker, it doesn't really help anyone. So we want to ensure that we access the correct resource. And you remember this comic from the 90s that on internet, no one knows that you're a dog. Actually, security services often know exactly who you are on internet, but how can we ensure that we know what are the resources that we access in the internet? This is really important. So this is a challenge. We need to prove ownership of resources in the internet. Basically, when you want to ensure security in the internet, you need cryptography, right? You need cryptography such as certificates which prove ownership of resources in the internet. A certificate is just a form, a digitally signed form which with my identity and the identity or description of the resource that I own, let's say a domain. So if you want to establish internet security, we need to have a cryptography. And if we want cryptography, we need to ensure that we can validate ownership over the resource that we're accessing. So think about this. Internet security requires cryptography. Essentially, this means we need a digital certificate which binds a cryptographic key to an identity. So to ensure security, we need this assumption that we have this certificate. But to have this certificate in the first place, we need to validate ownership. So this is like a circuit. In conceptually interesting problem. How do you resolve this? To establish cryptography, you need cryptography. This is exactly the question, and that's what I will see today. We'll see 2 examples. How can we establish identity or ownership over IP prefixes and domain names? I'll show you vulnerabilities which require doing this and establishing ownership over those resources or digital assets, in which case they are vulnerable and what should be done to ensure security. So we start with IP prefixes. Okay, so in IP prefixes are everything that we have in the internet, and I'll just talk about IPv4, is hosted on servers, which typically externally have IP addresses, which allows to access them externally. So what I will show you is IP prefix hijacks in internet, where someone else is claiming ownership over prefixes, and prefix is just a block or set of IPs which belong to some network. So I'll show you hijack attacks against IP prefixes in the internet. Then I'll show you that there is a solution which is called RPKI, which establishes certificates, which creates certificates that bind IP prefixes to owners. Then I'll show you that it's actually not really deployed, what are the problems and how we resolve them. So what is a prefix hijack attack? Here is an example of a prefix hijack attack, which was, if I remember, in 2015, but it was extremely publicized. And the problem with this attack was that it was going on for half a year, and at least half a year, and no one detected this. So let's look at the attack. What you see is two government offices communicating, Washington, D.C. and Guadalajara or something else in Mexico. So I just cannot pronounce it correctly. So these two endpoints, the green ones, they were communicating, and I don't know if you can see my mouse, but then I'm pointing at the one in Mexico, and it was sending traffic to the one in DC. And the green lines is the correct route that the packet should have taken to reach the destination. But what we see is the red route, and the red route is the hijacked traffic. So you can see from Mexico, the traffic was being sent to the next point still in Mexico, and then to Texas, and then to New York, and then it was sent instead of Washington, D.C. to London. It just a completely different continent, then to Moscow, and then to Belarus, and then to Frankfurt in Germany, and then was it sent finally back to New York and to Washington, D.C. So you see the traffic had to traverse such a huge route through a different continent to reach eventually being sent to the destination. And why did the attackers do this is because they wanted to avoid detection. If you send the traffic back or you relay it back to the destination where it was meant to arrive, then no one noticed anything. And this is surprising. You would say, well, of course it added a lot of latency to the communication. Nevertheless, nothing was noticed, and it went on at least for half a year. Attackers were redirecting traffic through Moscow, and they were picking up everything that was sent. If it was not encrypted, they could read it. If it was encrypted with weak cryptography that attackers could break, then it was broken. So routing attacks are extremely significant, and they happen thousands a year. You see, these are some examples of attacks which happen over the years. Now, we have thousands of those attacks a year. Many of them are misconfigurations, but many of them are real attacks. And how can you know if something is a misconfiguration or an attack? An attacker will not come and say, well, yeah, actually, I did this. I just wanted to see your traffic. Of course, they will try always to say that this was a misconfiguration. And especially from China, we see a lot of such attacks where they hijack traffic, but they argue that this was just a misconfiguration. And nevertheless, these misconfigurations go on over a long period of time, and the Chinese do not fix it and attract a lot of traffic, which creates a suspicion that maybe it's done intentionally, and intentionally don't fix it. So because prefix hijacks, or claiming prefix, in other words, claiming prefix which belongs to someone else, is such a significant problem, something should be done. And it is a problem. You know, all your traffic, no matter what you do, telephony or transactions or communications, chats, etc., it will all be sent through the incorrect route. So it's like a Waze or Google Maps, which, when mistakenly or intentionally you are sent through the wrong route. Let's say if you want to go from Frankfurt to Berlin, you go through Moscow. Of course, this is not good. So how do we fix this problem, and what are the solutions? There is resource public key infrastructure. This is an RPKI for short, and it is essentially a PKI for the internet, a PKI for IP addresses. We have two parts to RPKI, certificates and validation. And certificates bind an IP prefix, or as I said, an IP prefix is a set of IPs that belong to some network, to a public key. Certificates bind an IP prefix to a public key for short, and validation, essentially every network in the internet have to validate certificates. So when you see a BGP announcement, every network sends announcements about its reachability in the internet. And then when you see a BGP announcement about some network which says, I own prefix 1234, let's say 12/16, then you will be able to verify via a certificate if it really belongs to that network, or maybe it is a hijack. So this is how it's done. You can see here in the middle, BGP routers, border gateway protocol routers, which check which path packets should take in the internet. They will retrieve certificates from public RPKI repository, and then they will, every announcement they will see, they will validate against the certificate. And that's how they will know, is the announcement correct? Do I accept it, or do I filter it? So then let's look at how many networks actually have signed their prefixes or have certificates that vouch for the ownership of the prefix, so the owner of the prefix. We see that only 18%. Our recent measurements show that only 18% of the prefixes in the internet have certificates. So that's not bad, although RPKI exists already a decade almost. This is not was standardized over a decade. This is not bad, but still slow. But the more significant problem is that networks almost apply no validation over BGP announcements. So when I say send an announcement, almost no network, or in other words, less than 8% of the networks will check the announcements against the certificates. So you see, we have a decade in which RPKI could have been deployed, but it's still not happening. Well, notice RPKI is essentially digital signatures, and digital signatures have been existing over 40 years, right? We have digital signatures for ages. So we know how to do digital signatures, and definitely in cryptographic conferences and in other conferences, they're doing a cryptography paper, but digital signature is not a thing because it's a trivial thing to do. Look how difficult this is to deploy in the internet. And now you will see a few problems when you take just a simple mechanism like digital signatures, which we know how to do in theory, and let's look how we deploy this in practice. Okay, so you see, despite the fact that 10 years it is there are really few certificates. In 10 years, we could have issued certificates for many more prefixes, still only 18%, and almost no one validates. Let's look at the problems. One of the problems, or one of the most significant problems why certificates are not deployed and why validation is not created, is invalid certificates. So look at this chart, you will see that almost 1% of the certificates is invalid. Now you may say, well, it's 1% is not so bad. Actually, it means that most of the certificates are correct. Most of those which signed their prefixes did this correctly. It may seem so, but if you look again back, you will see that this less than 1% is causing hardly any validation of the certificates, of the BGP announcements, and people are not, networks are not really deploying certificates. Now, just to clarify, this is not an end user mechanism, and BGP is not an end user protocol. This is a protocol connecting networks to the internet, and certificates are needed for the entire prefix. So it's not something that I am as an end user, I can do, but a system administrator or a network does it for me. And those guys, they have this expertise, they should be able to do it. Nevertheless, we see there are many errors. Now, in our research, we found that actually there's many errors. I mean, almost 1% of errors, erroneous certificates, they are done by large networks. This means that these large networks, they connect many small networks to the internet. So the networks are typically in the internet split hierarchically. You have like tier 1 providers, and you have tier 2, and you have tier 3 providers. And tier 1 providers, they connect many smaller networks to the internet and provide connectivity for those networks to the internet, upstream connectivity. And if those networks have incorrect certificates, then this will, when routers filter this traffic, they will drop traffic of all those networks behind this large provider, or all those networks which receive connectivity from the large provider. One example is Swisscom. We measured 2 years ago, what are these large organizations or network autonomous systems or network providers which have misconfigured certificates. There are many in France, for instance, in Europe, and in Swisscom is one of them. So these are networks which should be able to know how to create correct certificates. Nevertheless, there are errors. And these errors, when you have erroneous certificate, or essentially when you have a BGP announcement which contradicts the certificate, or certificate which contradicts the BGP announcement, a router which does validation should discard this traffic. But notice, routing in the internet works according to financial motivation. So if I block traffic, I lose revenues. And if I block traffic of some provider, I will provide less connectivity, so I will make less money. So one of the main reasons why the deployment of RPKI is so slow, because people are afraid to lose business and afraid to disconnect networks from the internet. So networks will get disconnected when there are incorrect certificates and you lose your revenues. That's why almost no one does validation Now, this conflict between BGP announcements and the invalid certificates, they typically will look like a misconfiguration, like an hijack, but actually it is just a misconfiguration and an error. And most of them are a misconfiguration or an error. This is actually the case. And as a result, you not only get limited security benefits, but you lose traffic, you lose connectivity, and so on. So let's look at the causes. Why is this the situation? Why do we have errors? And we measured RPK certificates over a period of 3 years. And what we saw, as more networks get signed, so we started measuring when only 6% of the networks were signed or prefixes had certificates. And now it's 18%, right? So over a period of 3 years, what we see is as the number of networks that get signed increases, also the number of misconfigured prefixes or certificates increases. So there is a correlation. It means that no matter how much time will pass, there will always probably be errors. So what are the problems into this? What are the factors causing this situation? And here are the factors, how the causes. First, RPKI. To issue a certificate, you do a legal ownership validation. So the certificate authority in RPKI, which is actually called Regional Internet Registry, and there are 5 of those. And in Europe, we have the RIPE NCC. This is the CA. You can say this is the CA for Europe. And when they issue a certificate, they will do ownership validation over the prefix. Now, this ownership validation is done manually, and it's cumbersome and it's complex to prove that you really own the prefix. So you have to have legal documents, you have to prove that, you have to go, you have to send stuff, you have to fax. Very cumbersome, long time, and expensive. Now, you once you prove your ownership, the certificate is issued manually. And this manual issuance by people that work in this network, or the system administrator, or security experts, this manual issuance of certificates is error prone. Because there is a human factor, there is a lot of errors. So this is second problem. And the third problem, which you see the problems listed on the right side, the third problem, there is no feedback on errors. When you do an error, when you make an error, you do not know that you made a mistake. So there is no feedback on errors. And how can we solve these problems? What I will quickly explain to you is our mechanism, which we did for automating ownership validation in the internet. And our validation of an ownership is not legal, in contrast to the current process, which is legal process. We devised a de facto ownership validation for IP prefixes. So we have an automated prefix validation, if I really am the owner or not, automated issuance of certificates, eliminating errors and allowing distribution. I'm going to say just a few words about this, but if you like, you can send me, of course, emails, or you can see a paper. This was published at NDSS, this paper, last year. So essentially, the problem that I told you initially is how can you create security without having cryptography, or how can you create cryptography without cryptography? That was the problem. What we are doing is we're replacing this initial assumption for cryptography with the distributed nature of the internet. We placed agents in the internet, and they, once you want to issue a certificate, they will probe your network, and they will check that you can answer from different points to different points of your network. And they will check that you can answer to this probes, and if you answer correctly, they conclude that you are the owner. So notice the difference. This is a de facto ownership verification in contrast to the standard or custom current practice with legal ownership verification. And this legal, as I said, long and manual and error prone and so on. And this is an automated way to do this. Now you can see in this figure on the left side, you have an AS with our mechanism, which is called DISCO for short, Decentralized Infrastructure for Securing and Certifying Origins. And on the right side, you see the internet with our nodes and with our registrars. They will probe your network. You have to install our DISCO agent. This is the only thing that you have to do. There are no changes that are required to your infrastructure. This means that you do not need to do anything. You just install our agent. It will do the verification against the registrars, our registrars. Then in an automated way, it will notify the RIR, the Regional Internet Registry, or in our case, RIPE NCC, and issue a certificate for you. It will distribute your key publicly to everyone in the internet in an automated way, and everyone is able to verify your announcement. So essentially, this mechanism solves all the issues that I told you that are currently exist with the RPKI. So let's look at 3 significant properties in this mechanism. And we want to send a public key and distribute it to all the networks. How do we do it? What we did is we utilized a transitive attribute in a BGP announcement. This field was left for future developments and future mechanisms. So we use just a standard field that was standardized for different purposes, and we distributed public key in this field of a BGP announcement. So essentially, when a network sends its announcement, it distributes the key. Our registrars certify the public key, and what we saw is that, first of all, we need to see that the network can actually support this transitive announcement and relay the transitive attribute and relay the announcements which have the transitive attribute. Actually, there we identified how fragile the internet is when we were running these experiments in the wild. So we didn't do just simulations. We also wanted to see how the internet reacts to this. And there were buggy routers which failed, and the networks with those routers were disconnected from the internet. It actually caused quite a lot of mess in the internet. Although our experiment was approved by the IETF, by the research community, by NANOGs and different working groups, and we prepared everything, no one expected that in the internet there are unpatched or unstandard or non-standard compliant routers. And these routers, this essentially means that if an attacker would send just one BGP announcement, a single BGP announcement, it would cause the networks to disconnect from the internet. So a large fraction of the internet, of the networks really failed and disconnected, and we had to stop the experiment. But if you look at the graph on the right bottom side, you will see our experiment in January 7th. You see these 2 huge spikes. Yeah, this on January 7th, these are the spike which caused a lot of traffic or a lot of BGP announcements because of routers which failed to process our BGP announcement with a public key in a transitive attribute. So the field which was reserved for this. And so we notified the community. There was a lot of discussion within the IETF that how important such experiments are, and that one should really design mechanisms not just in theory and validate them with simulations, but you really need to see that internet can work. And I will tell you that this is just one example. Internet is not how we think it works. It's not in the textbook. It's not how the textbook systems or servers or services or protocols are described in the university. It works typically different. And this is, for instance, one example for this. You think that routers should be able to process everything that is standard, but they are not. Now, look at the orange line. In the orange line, which was done in the black line, which was done the day afterwards, you will see that the spike is much lower. And this shows that in really short time, all the routers were patched, or many of the routers were patched to be able to process this standard BGP announcement. We were not attacking the internet. We were just sending out a standard BGP announcement. So the routers were patched. That's a good thing. And but it essentially also means that one of the interesting research questions is how many outdated, not patched, non-standard equipment we have in the internet. And if we start using something which is not something that was used on an everyday, how much of the internet will crash? What fraction of the internet will crash? That's also an interesting, of course, problem. So this is one issue. So now currently, we say that we actually validated that only less than 1% of the AES's autonomous system will not support our mechanism. More than 99% of the network supported. This means that it can be deployed and run in the internet. Indeed, that's what we did. We deployed it in the internet. We work with the IETF on standardizing it now. And we integrated our validator into the RIPE validator. And we work with RIPE on making it widely used and deployed. Now, what we also want to show is when a network wants to certify itself, it will be able to certify its with high probability. It will be able to certify its public key. So we deployed agents, as I said, in different points in the internet. And these agents, when they see announcements with a public key, they will register that public key. What we show is that in simulations, of course, that more than 95% of the vantage points will see reported keys from any network in the internet. This means any network which will send an announcement, at least 95% of the vantage points will record it. And of course, another question is, what happens when an attacker wants to exploit our mechanism? to hijack prefix when it hijacks a prefix and then registers with our mechanism. So essentially to issue a certificate exactly during the hijack. And this could, of course, be a severe problem if this was possible. What we show is that such attackers will have less than 3% success, and this 3% success is only possible when the hijacker or when the attacker is your upstream provider. But if you have a malicious upstream provider, you're anyway doomed, and hijacking your prefix or registering your with Disco with our mechanism to issue an RPKI certificate, this will be the least of a problem for you, because he can do anything then and disconnect you from the internet and monitor your traffic and so on. So essentially we show that an attacker cannot exploit this mechanism to register itself. It was published in a few conferences, this project, and here you can see at the bottom, and if you want to read the IETF draft about this or read papers, you can let me know on. Okay, and so this essentially mechanism which we designed, yeah, it allows you to leverage the distributed nature of the internet to bootstrap cryptography. In a sense, we don't assume any initial cryptography. We bootstrap cryptography using the internet. We allow, by leveraging this distributed nature of the internet, to authenticate ownership of IP addresses. We automated issuance of certificates. This solves the errors and other problems as well. And that's for IP. I hope that it will be soon widely deployed, but we are working on this, and this is just the recent work. Now, actually, surprisingly, similar problems apply also to domains. So conceptually, the problems which apply to IP prefix and domains are similar. And even more surprisingly, the solutions which apply, which try to prevent domains hijacks, and are very similar to solutions, conceptually similar to solutions which try to prevent IP prefix hijacks. Technologically, they're different, but you will see that they are similar conceptually. So let's look at domain ownership validation for domains. So in domains hijack. So I will show you, depending on the time, I will show you as much as I can. Everything that I cannot show you, then technical details, I may leave for some other time. And this is the outline. So first, in contrast to IP addresses, which currently there was only one way to validate ownership of IP addresses, and this is this manual way. You have a contract, you prove that you bought this IP address, and therefore you're the owner. So there was this legal ownership. And what we did is we did a mechanism which did de facto ownership. Now in domain names, in contrast, there are two ways to validate ownership. And I'm talking about a PKI, a widely known PKI, which we use on an everyday basis, right? We have certificates which certificate authorities issue, and there are hundreds of certificate authorities and browsers, and there are different ways to issue the certificates. There is the legal approach, and there is the de facto approach. And in certificates, the de facto approach is the most popular one. I believe this will be also the case for IP addresses, and you will see in a minute why. So legal approaches. What is the problem with legal approaches, and why they are not so widely used? They're manual, they're time consuming, and most importantly, they're extremely expensive. You have to do a lot of things, it's cumbersome. And one example for legal approaches are extended validation or organization validation. What about de facto approaches? A de facto approach is an automated validation of ownership over resources. So it's not a legal validation, it's a de facto validation. This means that I check that you can de facto respond on behalf of that resource. You remember, with our mechanism for IP addresses, what we checked, we sent challenges to the IP addresses in that block, which you claim you own, and we wanted to see that you are able to respond to these challenges. So this doesn't check if you really are the owner, but it checks if you are de facto owner. So maybe I outsource to you management over my IP addresses. I have the contract which says that I bought the IP addresses, but you de facto manage and operate them. So that's the de facto ownership. And in domains, de facto ownership is also the most popular approach. Here's an example when you issue a certificate using Commodore, how it works. So what you do, if you have a website, you have a service, and you want to allow everyone to access your service, and you want to allow everyone to encrypt or protect communication to your service. So what you do is you issue a certificate by going to certificate authority. Let's say you decide to use Commodore. Here's an example print screen of Commodore. You need to submit a certificate certificate signing request form. This is the certificate signing request form. If it plays now, okay, for some reason it doesn't play online, but I will then tell you, and believe me, simply you copy the CSR into this field, and the CSR contains your information about you and the information about the domain that you want. So let's say you want a domain for deutschebank.de, and this is the domain which you want. You enter your information and the information of the domain and the public key, and then from this will be created a certificate which will be signed by the certificate authority. So far, so good. Now, on the right hand, you will see that there is another form. Once you submit the CSR, the CA will do an automated validation of the ownership over the domain for which you want to issue a certificate. If it was not doing this, of course, this would have been really bad, because I or anyone else could claim ownership or issue certificates for resources which they do not control. So we do not want fraudulent certificates. Therefore, CA will perform a validation. CA will create here, if this video works, then you will see, but this video for some reason also doesn't work in Zoom. Good. So the CA will generate a challenge which it will then test that you can respond with, and echo this challenge to the CA from your domain. So there are different ways to do this. It could send over email. It could ask you to integrate this into a web page on your website or into your name server. Doesn't matter. Essentially what this means, the CA issues a challenge, and you take this challenge and you prove to the CA that you really received the challenge. And the point is that only real owner of the domain should be able to receive this challenge, but not the attacker, because he doesn't control the domain. So this is a de facto ownership, because I don't show you a contract that I'm really the owner, but I prove to you that I really control the resource and I can respond on behalf of this resource. If you send me a challenge, I respond to it. Now think about the following. If the attacker can hijack this validation, this called domain validation, this procedure, and by the way, is supported by more than 95% of the certificate authorities, supported by almost all the certificate authorities in the internet, and definitely by the most popular certificate authorities, which only use domain validation, which control more than 95% of the certificates market. So I'll show you an attack which we did with an off-pass weak attacker. So the problem with this, or the goal of this PKI, web PKI, is to provide security against very strong attackers, man-in-the-middle attackers. I will show you that we could subvert the security with an off-pass attacker. An off-pass attacker, in contrast to a man-in-the-middle attacker, doesn't see the traffic that traverses it. The traffic is somewhere else, and it can try to modify or alter this traffic remotely and attack it. Let's see how it's done. So in this case, the attacker submits. This is a very high-level description, and I will show you in a second details if time allows. Attacker sends a certificate signing request to the CA. CA performs domain validation against the domain which the attacker wants a certificate to issue a certificate for. In this case, the attacker wants a certificate for a victim domain, victim.org. And if the attacker manages to intercept the validation, it will convince the certificate authority that it is really the owner, and it will then receive a certificate which will be signed for the victim.org domain of the victim, which will be signed with the attacker's public key. And that's really bad, because it means you will be protecting your communication to the attacker instead of the real domain. Now, notice the problem with this PKI is really significant, because you have hundreds of CAs. This means even if one CA is vulnerable, the entire PKI ecosystem is vulnerable. But actually, in this case, it's more than one CA is vulnerable. So we demonstrated this attack against popular and widely used CAs. Here is an example of the CAs which we tested. And you can see that they all support different type of domain validation via email, DNS, HTTPS, or whois. Doesn't really matter what the details are. Essentially, these are popular and widely used CAs which are vulnerable. We communicated also with those CAs, and they are deploying countermeasures. One of the CAs, Let's Encrypt, is also deploying a mechanism which we proposed in the paper, which was published at CCS in 2018. So let's look at the attack a little bit more in detail. I'm going to briefly skim through this attack. I know that this will not be clear, but unfortunately, we do not have more time. So those that have questions, I will be able to simply send the paper. Good. The domain owner issues a certificate sign-in request for its own domain, a.com, to the CA. And this in the square, you see the CA simplified presentation with two resources, a DNS resolver, this is a cache, and a web server. A web server to which you submit the request, and DNS resolver will do the domain validation, or does the domain validation. First of all, DNS resolver will ask for the IP address of this requester of a.com, and will receive from a name server, from the com domain, an IP address saying 1234, and will cache it. You see now in the cache, there is an IP address 1234. It's all simplified, okay? So those of you who know the details, just I'm omitting a lot. Okay, and then as soon as there is an IP address in the cache of the DNS resolver, a domain validation confirming control over a.com will be done against this domain owner. Now, what happens if an attacker injects a malicious entry, an entry saying the IP address of a.com is 6666 via DNS cache poisoning? Then the validation will be done against the attacker and not against the real owner. Domain validation will be done against the attacker, and the attacker will receive a certificate for a.com with attacker's key. And that's in a nutshell the attack. Now, but how do you do this DNS cache poisoning? Can you just send an IP address, an incorrect IP address, and it will be accepted by the resolver? Then this means that all the internet here is vulnerable and it's really bad. Of course, it's not so trivial. Now, DNS uses a mechanism to protect such attacks against off-path attacker, and the mechanism which it uses is called cookies. It uses random cookies which are sent in request. It's not like the cryptographic challenge response that you know, which when you receive, you have to calculate something like a hash and return it. It's something else. Look at the bottom right side. Bob sends a cryptographic challenge with sends a challenge which is a cookie, which it selected from a jar of cookies. You see at the bottom, at the top here in the middle, there is a jar of cookies, and DNS uses two types of cookies, source port and DNS transaction identifier. Both are 16 bits, and overall it gives you 2 to 32 bits of randomness. And if you select these cookies from such a large jar, 2 to 32 is a large jar, the attacker will not be able to guess the cookies. So the correct ones. So Bob sends to Alice here in step 1 a request with a cookie, and Alice sends a response and echoes the cookie in the response. Bob validates that the cookie is the same one as he sent, and he accepts the response as authentic. If the attacker, you see the attacker also sends something impersonating Alice, but he sends a wrong cookie because the jar is so big, then Bob will not accept it. And trying to send many different responses with different cookies isn't practical because the attacker will not be able to go through this huge jar of 2 to 32 cookies. And this is exactly what happens with DNS. When a DNS resolver, you see here up right top, when a DNS resolver sends a request for a.com to the name server, it will select a cookie from this large jar of cookies, and when the attacker sends a response, its response with high probability will not contain the correct cookie, and therefore the attack is not practical. But actually what we did is we designed a technique to bypass this using an IP layer in the internet. So briefly, 2 words about fragmentation. Networks, each network supports a maximal size of packets which they can send to each other. And when the packet exceeds this size, it will be fragmented. So you can see a packet from Alice is fragmented to 2 packets because it was too big, and they will be reassembled at Bob, at the recipient. But now notice when you fragment the packet, all these challenge response defenses, which are in the headers of packets, they will stay in the first fragment. And the second fragment is then not protected. So the idea of our attack, we send a malicious second fragment, for which we do not need to guess anything. There is no challenge response. There is nothing random there. And if it's correctly constructed, it will be reassembled with the correct first fragment. And so we can inject invalid malicious entries. So here, when the packet, here's a format of an IP packet when it's fragmented, IP packet with DNS, yeah? So with DNS packet above it. When it's fragmented, you see the payload with all the queries and answers and IPs is in the second fragment, and the source port and the transaction identifiers in the first fragment. So this means we don't need to guess them at all. So we don't attack the randomness, we just bypass it. And here's how the attack is done. The attacker injects a malicious second fragment to the DNS, and it does this in advance before it starts anything. So there is no race condition. The attack is very simple. You send a second fragment, and in the second fragment you put payload mapping the domain a.com to a malicious IP address of the attacker. It's sent to DNS. The DNS caches the second fragment, you see, and it's waiting. The IP layer will cache this fragment for 30 seconds by default. And if it's not reassembled with any first fragment, it will be discarded after 30 seconds. But notice in this case, the attacker then triggers the query for a.com with a cookie, which is sent, of course, with a cookie. When the name server responds, it responds with 2 fragments, 1 and 2, the gray fragments. Now, the first fragment, 1, will be reassembled with the fragment that is waiting in the IP defragmentation cache of the DNS. If it's reassembled, it will go to the upper layer, and the malicious records will poison the cache of the DNS. So actually what you saw before that, you remember this messages exchange, what I showed you, you do the certificate sign-in request, then domain validation is performed, and then you intercept the domain validation. But this is just a logical presentation because the attacker does the attack before that. It plants the second malicious fragment, spoofed fragment into the cache, in the IP defragmentation cache of the DNS before the attack starts. And then when it starts the certificate sign-in request and domain validation, this is already reassembled. So the validation is already performed against the attacker and not against the real owner of the domain. So you can see the challenges, technical challenges, some selected technical challenges on the right side, but essentially these are all can be overcome. And we demonstrated the attack in the IETF and showed it against, also demonstrated to different CAs and showed to be practical. Just one word about the solution. I'm not going to go in depth, but it's really similar as well. We need to here do cryptography without having cryptography, but we need cryptography. So what we do, we utilize the distributed nature of the internet, and we just enhance the domain validation with distributed domain validation. So the idea of domain validation is excellent. This is a great mechanism. It saves money, it's cheap, it's really quick. You don't need to do anything. It's done, everything done for you. So we do distributed domain validation. Now, both our mechanisms, this and also for IP, it doesn't require changes in the internet infrastructure of the existing CAs. So it's extremely easy to deploy because for the CA, they use the same interface, but everything is done inside this black box of our mechanism, which is distributed. Yeah, the validation is distributed, but the interface to the CA or to the user hasn't changed. Okay, so I showed you 2 issues. I showed you essentially that there are digital resources or assets in the internet, which we all need for any service that we can imagine. We use those digital assets, and the most important ones are domains and IP address. And we want to be able to bind between owners and these assets. How do we do this? In IP, this is done manually. It's cumbersome, expensive, difficult, very long, and causes errors. And as a result, it's not really used. For DNS, for the web PKI, the situation is better because it's much more widely used and by end users. So there is domain validation, but it was vulnerable. So we showed actually that you can bypass or circumvent this need to start with cryptography just by using the internet. And then you can perform this validation or ownership of different assets and issue certificates in an automated way. As a side note, we also saw different problems in the internet. One of them, which I mentioned, how fragile routers are, that our experiment, which we didn't want just to do simulations with our mechanism, we really wanted to see that it works in the internet. And our experiment with this mechanism caused networks to crash and disconnect, of course, not because of us, but because the networks were not compliant, had routers which were not compliant with standard requirements for BGP routers. So this also means that there is a lot of need to look into the internet to understand the infrastructure, understand what is used, what should be patched without causing the internet also to crash. Thank you very much. Are there any questions?
Maybe I'm too late. Thanks a lot for your presentation, Haya. And admit I had to miss parts of your presentation because we are strongly debating some legal issues here. I think, will you share your slides with us?
Now? Or
no,
sometime.
afterwards.
Yeah, of course, no problem. So
And
I want to apologize to the public, but to the public?
Audience.
To the audience. I want to apologize to the audience that I was so fast because I thought I have more time at the beginning, and then I realized that I only have 45 minutes, and that's why I hope that you managed to pick up everything I said, and if not, really, I'm happy to answer questions. Feel free.
No, I valued it that you omitted lots of details. I think I think I understood surprisingly a lot from what you presented to us. And if you would have given us the details, then it would have been harder for me switching back in and back out to really understand the full picture. But I will go through it after all this General Assembly thing.
Okay.
During the weekend, and maybe I address you and I ask everyone else that I think you offered to send out your publications, and we'll do it.
Yeah, if anyone wants to read papers or to talk about it or more information, I'm happy to, of course, to provide this. We also have automated tools which we generated and they are online available for all of these issues. If you have, for instance, a network which has a misconfigured certificate, you can evaluate it in an automated way without having to understand yourself how it's done. We have a tool which is running in the internet. You can access it. It will tell you if your network is protected with RPKI, if the certificate is correctly configured, if there are errors, what you should fix, and so on. And similar, we have a tool which checks if there are vulnerabilities in a cache in the network that you are in the DNS cache. So essentially, we didn't just do these mechanisms which solve the problem, but also we designed tools and made them publicly available to allow anyone to check if they have vulnerabilities.
I think that's great. Just looking from distance at what you're doing, I was very impressed, which is why we were very happy that you joined us today.
Thank you.
Many thanks from Bern and many thanks from Switzerland to your presentation, and hope to hear you at another event of SI soon again. Thank you.
Excellent. Thank you very much. Bye-bye.